just arrange things here. Yeah, so thanks everybody for tuning in from wherever and whenever it is for you. It's great to be here. Thanks so much to the organizers for the invitation. I'm Brendan. I'm going to kind of kick things off here with an introduction to Federated Learning, and then I'll turn it over to Kallista and Peter to go into a little more detail on some of the privacy technologies related to Federated Learning. So we want to talk a little bit about what federated learning is at a high level and what some of the motivation was when we first started thinking about this. And really one of the core initial observations was how much interesting and useful data was being born at the edge, thinking about mobile phones in particular, right? These devices have all kinds of sensors, cameras, microphones, GPS, so they're very tapped into the real physical world, but they also kind of mediate many of our digital interactions and much of our communication as well. So that's an extremely rich source of data. You can use that to build amazing products using machine learning, but at the same time, that data can be highly privacy sensitive. And so what can we do with that? One of the trends that was already happening at the time we started thinking about federated learning was data processing was increasingly moving to those edge devices, to mobile phones, right where the data is, with lots of advantages: improved latency, apps that work offline, better battery life, as well as privacy advantages. So think of models like for next word prediction on a keyboard. You actually want those models running on your device for a lot of reasons. But this raised a couple of really critical questions, right? We use data not just for kind of inference and making predictions, but those models have to come from someplace. We need to compute metrics to understand how people are actually using products in order to make them better. So what should that look like in this world where data and increasingly processing is happening on the edge? So that's what got us thinking about, can we actually do machine learning in that setting? So that was the genesis of this idea for what we're now kind of calling the cross-device flavor of federated learning. We leave the raw data on devices, but we still want model engineers kind of working through a central server to be able to train models, evaluate models, and deploy them to edge devices. But as soon as we started, actually, yeah, so let me just say briefly what some of the good applications here. So what kind of problems can we use cross-device federated learning to solve? Well, we're interested primarily in problems where the data you have access to on device is more relevant than whatever you have on the server. If you have the data on the server you need on the server already, that's probably going to make things a little bit easier. Then we're also interested in machine learning problems where the data is privacy sensitive or large. So there's a good reason not to centralize it if you can avoid that. And finally, and this is a limitation that's increasingly being addressed by new research, but a lot of our focus have been on problems where the labels can be inferred naturally from user interaction. So think about things like language modeling for mobile keyboards, where if you don't predict the next word that a person is going to type correctly, they'll type it, and that becomes your feedback signal for the model. Or think of kind of image classification, where you're not predicting exactly what's in the image, but just whether or not people will share that image. That feedback signal is again kind of implicit in the user interaction. So we've been using this extensively at Google across a range of products. The first one where we engaged really deeply was with Gboard, Google's mobile keyboard. And as one example here, we launched a federated learning trained next word prediction model. And because we were training on kind of a better data source, we were able to get much higher accuracy compared to the baseline. So we were actually able to get better privacy properties as well as better accuracy. And this is representative of what we want to achieve with federated learning. And since then, we've used federated learning in Gboard for a bunch of other problems, including predicting emojis, different kind of actions, learning new words for expanding the vocabulary, and so on. And of course, this isn't just happening at Google now. Apple and others have also announced that they're using federated learning to solve a variety of different kind of privacy-preserving machine learning problems. But as soon as we started thinking about this and other people started hearing about it and thinking about it, it became clear that mobile devices weren't the only domain where you might want to leave data decentralized and do privacy preserving machine learning, where some set of clients kind of want to maintain control of their own data. In particular, we started thinking a lot about cross-silo settings as well, where the clients, instead of being mobile devices, are maybe whole institutions. So in the end of 2019, when we were collaborating on this really big survey paper, Advances in Open Problems in Federated Learning, we spent a lot of time trying to come up with a definition that isolated the key aspects of federated learning while opening up and being inclusive of this wide range of applications that people are working on. So this is what we came up with. Federated learning is a machine learning setting where multiple entities, clients, collaborate in solving a machine learning problem under the coordination of a central server or service provider. Each client's raw data is stored locally and not exchanged or transferred. Instead, focused updates intended for immediate aggregation are used to achieve the learning objective. So we can break that down a little bit. The kind of most important defining characteristics here, the first is that local data generation and the fact that that data remains localized, remains decentralized throughout whatever computation is being run. And a particular property of this is that that data tends to not be identically or independently distributed. Each client has their own data based on, say, their own usage of the app, which can have significant algorithmic consequences. And then we assume that there's some central orchestrating server or service provider that's kind of coordinating the training, but without seeing the raw data. So this allows us to include, as I was saying, cross-silo federated learning, where the clients are now institutions, maybe hospitals wanting to collaborate in solving a medical research problem, for example. And we've seen increasing interest in this application of federated learning. So here's a bunch of headlines about some of the work that Intel has been doing, targeting various medical applications. NVIDIA has also been very involved in this space. Again, healthcare is a primary motivating application. You'll also see self-driving systems and other problems being addressed. So I think one of the things that's most exciting about federated learning is this is very much work that's rooted in trying to solve a real world problem, right? We're trying to allow society to benefit from really high quality machine learning models that make all of our lives a little bit easier while doing that in a privacy sensitive way. And so I think from a research perspective, that means there's a real opportunity here to do impactful work that actually changes the way machine learning is done in industry and around the world. But that also means that research has to be focused on the actual problems that come up in these scenarios. And that's why I think it's useful to kind of contrast some of the differences between cross-device and cross-silo federated learning. They're both very much in the same spirit, but there's a lot of differences that may have a big influence on which classes of techniques make the most sense. So I'm not saying that one of these is better or more important. It's just that the constraints and characteristics of these settings, despite the similarities from that overall definition, can be quite different. So for example, in cross-device federated learning, we often have millions of intermittently available client devices, where for cross-silo, typically we're talking about a small number of clients here, institutions and so on, that have relatively high availability since they're, say, hosted in a data center. In the cross-device setting, those clients can't be indexed directly, so selection is necessarily coarse-grained, and the updates are typically completely anonymous. Whereas in the cross-silo setting, each client has an identity or name that allows the system to, say, access it directly. That's a reasonable assumption to make. So as a consequence of this, in the cross-device setting, the server is going to only be able to access a small random sample of clients on each round. And if you have a large population, that means most clients will probably only participate once in a single computation. Whereas for the cross-silo setting, since it's a small number of clients, most of them are going to participate in every round. And so running algorithms where clients maintain round-to-round state becomes feasible. whereas that wouldn't really make sense in cross-device, where the set of clients is continually changing and you may never see the same clients a second time. In cross-device setting, communication is often the primary bottleneck because wireless networks and home Wi-Fi connections are still relatively slow, whereas it's less clear in the cross-silo setting. And finally, the organization of the training data may be different. In the cross-device setting, we usually assume horizontally partitioned data, where each device has kind of complete training data, the complete set of features for each example. Whereas in the cross-silo setting, you can also consider kind of vertically partitioned data, where different institutions have different features for the same example. So this obviously requires very different algorithms that are doing some kind of joining. And then I wanted to just briefly contrast both of these with kind of distributed data center machine learning, which on the surface looks similar. The main difference there is that here we have kind of complete control of the data, and so any client or worker machine can kind of sample the data arbitrarily. That's one of the key things that's not true in federated learning and that we need to address. I think I've already kind of covered this, and I'm just going to put these slides in for reference. These basically summarize the same points I was making. This is taken from a table in Advances in Open Problems in Federated Learning. The last setting I wanted to briefly contrast federated learning to is kind of the fully decentralized or peer-to-peer learning scenario, where you have kind of an arbitrary topology of devices connected. And there's kind of a gray area between federated learning and fully decentralized peer-to-peer learning. You can certainly do fully decentralized learning that's in the spirit of federated learning. But one of the challenges here, especially when it comes to talking about privacy, is you have to figure out how kind of the person training the model, deciding which model is trained, and then doing something, and at the end, how do they actually interact with this system? So that's one of the main differences there. So now, since this is what we've worked on the most at Google, I wanted to dive into cross-device federated learning in a little bit more detail. And the first thing to point out, or to start from, is what do people do if they're not doing federated learning, right? What's the model development workflow? Of course, it starts usually with cloud data, and you train and evaluate your models on that. So you probably train a lot of models, hyperparameter search, a bunch of evaluation. Eventually, you get a model that you think is good. It's ready to deploy to production, say to mobile devices. And so you do some additional model validation steps on that to make sure that it has all of the production properties you actually care about. And then finally, the third step is actually shipping that final version of the model out to mobile devices, say for on-device inference. And in federated learning, most of that workflow we want to be the same. In particular, the final model validation step and the deployment steps don't have to change at all. We're really interested about changing the training and evaluation steps because those are the ones that actually require potentially touching private data in order to train the highest quality model possible. So we're looking to enable training and evaluation, maybe not just of a single model, but replacing the whole workflow of training grids of models to tune hyperparameters and do model selection and so on, replicating that in a federated setting. So there's a lot of just kind of API and developer experience challenges there. But really the core step is the federated training of a single model. So let's zoom in on that. And this is usually initiated by the device when the device meets eligibility criteria like being plugged in on a free Wi-Fi network and so on. It'll connect to the server and ask the server if it needs to do any work. And most of the time the server will say no, but sometimes the server will have a model it's trying to train that device can help with. So in that case, we start in the device download, say an initial version of the model. It might be completely randomly initialized, and run some machine learning infrastructure on the device, say a mobile version of TensorFlow, to process local data and come up with an updated version of that model. And that updated model is ephemeral. It's never used on the device to make predictions for the user, and the server isn't going to maintain it either. And this is an instantiation of a general privacy principle of focus collection. So we're not sending the raw data, we're only sending this model update or this updated model that is designed to get improved performance on a very specific task. And again, as I said, we're not going to persist these, which is another kind of data minimization privacy principle. And of course, we don't have just one device doing this at a time. We have hundreds or even thousands of devices all computing updates in parallel. And then the server is going to aggregate those updates as soon as possible. And the model engineer who's training this is never going to see any individual user's model update. They're only going to get access to that kind of final aggregated update, whether it's metrics or the model itself. And then it's going to take many iterations of this to train the final model we're looking for. So typically maybe thousands of rounds at 1 to 10 minutes per round. So we're looking at a few days to train a production quality model using this, this approach. And I'll just say briefly that federated learning describes the overall setting. One of the most common kind of training or optimization algorithms we use here is federated averaging, which is one of the simplest things you could think of. It just involves the devices running stochastic gradient descent locally to update the model, and then using a simple weighted average to combine those. But since we first started doing this, there's been a lot of developments on kind of the optimization side of federated learning, and so there's a lot of fancier algorithms you can try now that sometimes work better. Peter, do you want to say a few words about the extension to federated analytics?
Sure, yeah, thanks, Brendan. So like federated learning, we can actually also talk about federated analytics. So next slide, please. Okay, so for instance, some of the applications that we may be interested in practice are building geolocation heat maps. For instance, we would want to study how infectious diseases spread over a certain region, or try to discover frequently typed words out of dictionary words, trending words. For instance, COVID-19 is now trending. How do we discover very quickly what people are interested in? A large population are typing on their keyboard and add it to the dictionary so that we help them typing these new words. Things like popular songs, trends, and activities, and so on. Next slide, please. All right, so federated analytics is the practice of applying data science methods to the analysis of raw data that is stored locally on users' devices. Like federated learning, it works by running local computations over each device's data and only making the aggregated results and never any data from a particular device available to the product engineers. Unlike federated learning, however, federated analytics aims to support basic data science needs. So let's see a few examples of these data science needs on the next slide. So things like histograms over closed sets, or computing quantiles, or finding, counting the number of distinct elements, discovering heavy hitters over open sets, or density vector spaces. And in fact, you can try to generalize this to any SQL-like operation that a data analyst is used to, or maybe even broaden it even more to arbitrary computations over massively decentralized data sets. And the space is open, so you can think of lots and lots of other analytics applications. Next slide, please. So very briefly, I wanted to also give you two flavors of federated analytics algorithms. So the first one is interactive, and this is very similar to what Brendan was describing for federated learning. Here, the server maintains a state, so what it has learned so far, and in every round, it broadcasts that state to a subset of the available clients. And based on that state, the clients would compute a focused minimal update and send it back to the server. And the server would use those updates from the client in order to update the state. And you would go on in rounds. This is interactive because there is statefulness. So we're updating that state from one round to the other. And for instance, one example algorithm in this space is the federated heavy hitters discovery algorithm that appeared in AI Stats 2020. This is used in order to discover frequently typed words on people's keyboards, or any other, frequently typed or frequently used items, and it learns them by learning popular prefixes sequentially. Another class of algorithms for federated analytics are non-interactive in nature, meaning that there is no state on the server. So here, what happens is there's no need for the server to broadcast a state that it has learned so far. The users would compute something on their data locally. For instance, they would sketch their data, put it in a small Bloom filter, and then only send that focused small sketch to the server, which the server can use to compute those statistics. And one example that has been around from Google for a while is Rapport to learn histograms or even heavy hitters over open sets. And one big question in this space is whether or not the use of interactivity is useful in order to improve the privacy, accuracy, communication trade-offs. So this is a big question that we encourage the community to look at and work on, and settle some trade-offs across a variety of analytics tasks. Thanks.
Thanks, Peter. All right, with that in place, let's dive into kind of the privacy for these technologies. I think, as we've already seen and discussed a little bit, this privacy can mean a number of different things. So I wanted to start with kind of a fairly zoomed out view of different aspects of privacy. And this is just one way to present that. One of the kind of core parts of privacy is, why are we using this data in the first place? So this is around transparency and consent. So key to having privacy is that the user understands and supports the intended use of the data. The next thing we might ask is kind of what is actually being computed or what is being released. When that data is released, we want to ensure it does not reveal any user's private information. So we want to limit the influence of any individual on, say, the final model or the final metrics we're releasing. So this is where differential privacy in particular fits in. But the way we're using the term privacy here, we mean this larger space. And another critical aspects of privacy is kind of the how of the computation, the how and the where of the computation happens, right? So we want to release that data to as few parties as possible. We want to minimize attack surfaces where private information can be accessed. So for this talk, we're not going to spend much time on the why, because we're going to focus more on the algorithms and the technical aspects, the technologies that are critical to the what and the how questions. I think everybody here probably understands that there can be a tension between privacy and utility when you're doing machine learning on sensitive data, right? There's some trade-off curve. Now, I think the perception is that we're somewhere very far on the high utility side of that trade-off curve. I would say that we're actually, at least based on what I've seen from what we're doing at Google, in a fairly reasonable place. But it's still there's still hard choices to be made there, and that will probably already be the case. But as developers of new technology, the goal of my team and a large number of teams working at Google is really pushing out that Pareto frontier of what's possible. We want to make it as possible as we can to get high privacy and good utility. There's still important questions to be made about, for a particular product or application, what's the right combination of technologies to use, where on this trade-off curve is the right place to be. And that's something that where researchers have a critical role in that conversation, but it's not a decision that researchers can make on their own, right? There's a lot of ramifications there. The other point I wanted to make here is that this isn't really just a two-axis trade-off, right? There are a couple of other things here that are actually really important in practice. One is that there's a trade-off in terms of the amount of computation you have to do. Often, if you have a large enough data set, you can get arbitrarily good privacy versus utility trade-offs if you're willing to do enough computation. But there's a question of what's the cost of that. And then there's also kind of an effort question from the point of view of the ML engineers that are working with this technology. How much more work is it to work with technology that provides strong privacy guarantees? We want to get that barrier to entry down as much as we can. So those are kind of the goals and the broad framing of what we're trying to do. We're trying to introduce kind of a variety of privacy technologies here that give us better options. Now let's dive in a little bit into kind of what are some of the threat models we might have. And I think we're obviously going to do this exercise for federated learning, but this is really something that you can and probably should do for any system that's processing privacy sensitive information. So I like to frame this in terms of thinking about what private information might some actor learn with access to different parts of the system, right? What about physical access to the device or physical access to the network? What about, root access to the server? What if you just get to see that the models and metrics that we release, say, to the engineer? And finally, what if you have access to kind of the deployed model that we ship out to millions of Android devices? Obviously, kind of the chance of somebody having access to these different parts of the system is very different, right? Hopefully, a very small number of people have root access to servers, say at Google, whereas the deployed model we're essentially making fully public. So we may need different considerations or different kinds of guarantees for these different access points in the system. And I'll just say that another way to kind of frame this question is you can also ask, how much do you need to trust kind of these different parts of the system? Or what can these different parts of the systems do in order to prove they're behaving correctly? And we've already seen that federated learning is kind of designed to follow certain privacy principles, primarily in terms of the how and the where of the computation, right? We're minimizing data exposure by keeping the raw data on device, not also logging it. We're doing focus collection to send updates that have the minimal information. Those updates are anonymous and ephemeral. The server is aggregating as early as possible and minimizing the retention of any of the intermediate computation states. You could say, though, that only an aggregate release, only releasing aggregates of data rather than individual data, that is about kind of what we are releasing, but it's certainly not going to provide, say, a differential privacy guarantee on its own. And so we can kind of go through this list of potential threat models and then think about what additional technologies we can use to provide stronger guarantees. So encryption at rest and on the wire, on the device and on the network, is kind of table stakes for any reasonable solution in this space. And that actually goes a long way. Really, kind of somebody with physical access to the device or the network doesn't need to learn anything in order for us to accomplish our goal, training the model. And so we can just kind of use crypto to rule that access out, assuming the crypto is implemented correctly. Things are a little bit trickier on the server. The server has an important role to play in this computation. One approach here is local differential privacy. This is, again, using kind of a what to compute approach where each user sends noise data to the server so that the server can't learn anything too useful from any one user's update. But this can have pretty severe consequences in terms of utility. And so we can also kind of step back, though, and say, hey, what does the server kind of need? What does somebody with access to the server have to learn intrinsically to solve this say machine learning problem? And the answer is that they shouldn't have to learn anything. So can we just make that the case? And the answer is maybe. There's technologies like secure enclaves and secure multi-party computation that can help address these concerns of trust with the server. And we're going to hear more about that in the next part of the talk. Moving down through the system, what about the released models and metrics in the deployed model? These things are different. We have to actually kind of put those bytes out there. The engineer needs to be able to interact with the model and the metrics to do their job. We need to be able to actually ship the model to device and show predictions from that model to the users. So this isn't something where the how and the where of the computation can provide the privacy guarantees we want. So this is the classic example of where, say, central differential privacy applies. We want to make sure that even if you have access to those released aggregates, you can't learn too much about any one individual. But there's other very complementary technologies here. For example, empirical privacy auditing. Even if we don't have a differential privacy guarantee, or maybe the epsilon is larger than we would like, we can actually do empirical testing of those models to see whether or not they have memorized any data from a particular individual. So this can build a lot of confidence that our system isn't leaking privacy, and is very complementary to differential privacy guarantees, because this is actually kind of testing the full system end to end. So that kind of outlined the broad privacy landscape, and with that, I will turn it over to Kallista here.
All right, thanks. Can everyone hear and see?
Sorry to
sure.
interrupt. I wonder whether I can read this some questions that came into the chat, because they're related to this section.
Yeah, please.
That's great. So there's a couple of questions from Vijay. So the first is whether there is a filtering of device based on the number of new training data samples in federated learning.
Sorry, a filtering?
The number of new training data samples.
I think in the device selection stage, Brendan.
Let's see. Yeah, so that's certainly possible. You know, that would depend on the details of the particular federated learning infrastructure you're using. There's some coverage of that, I think, in our paper towards federated learning at scale for what we do at Google. But in general, I think the right way to select clients to participate in FL is a really interesting question. The thing to keep in mind there, though, is that the server has a very limited ability to kind of control that. The first order determination is the strict eligibility requirements for devices, so that we don't negatively impact the user experience. But certainly, like, it doesn't make sense to have devices that don't have any data connect and participate in training, because obviously they wouldn't contribute anything useful.
Thank you, Brendan. And the second question is, how is the initial model chosen?
Yeah, that's a great question. There's a couple of possible answers to that. So what we've done in most of our research papers, and sometimes in practical application, as well as you just start as you would typically with a deep learning model with some random initialization, right? And you can train models completely successfully from random initialization using federated learning. However, in many cases, you might have, say, a public data set that isn't drawn from quite the right distribution, but you want to, say, train a text model, and we have large public text corpuses from web crawls and so on available in the data center. So in that case, pre-training a model on the public data and then using federated learning for fine-tuning can also be a really useful technique.
Thank you, Brendan. I'm going to give the mic back to you, Kallista.
Great, thank you. All right, so in this section of the talk, we're going to be discussing private aggregation and trust. And this is kind of addressing the how part that Brendan was talking about earlier. So when we think about distributing trust and minimizing the amount of trust you need to put in any particular system, really this aggregation stage is one of the most important components to look at. Now, in the description that Brendan had given, we were talking about the server being the party that's responsible for doing the aggregation as well. You can actually separate out that responsibility and imagine having a completely trusted third party that aggregates all of the model updates from all of the users and only hands the result of that over to the coordinating server that's running the rest of federated learning. And if you have a mutually acceptable, fully trusted third party, this is a great solution. Unfortunately, these can be hard to come by in a lot of circumstances, so it's good to have some other options as well. One thing you can do is use trusted execution environments or secure enclaves in order to basically simulate one of these trusted third parties. You have a special piece of hardware that has security properties baked into it that prevent even the owner of the server and someone who has root access to that hardware from making it do something other than what it's supposed to do. So it can provide guarantees to the client devices that are interacting with it, that it is running a particular program, that it runs that program without revealing any information to the outside world that it's not supposed to, that the root owner of this hardware can't tamper with the running of that program. And it can make all of these guarantees in a way that the client devices can verify before uploading their data to that enclave. So you could run your aggregation procedure inside of there on the server, but the rest of the server, the running outside of this enclave, provably would only get to learn the aggregate. And this all works assuming that your hardware has been implemented correctly and that you trust the hardware provider to keep their appropriate secrets safe and such. Now, if you don't have access to hardware that you can trust, there's another option, and that's to use cryptography. And basically, in the cryptographic approach, this is a branch of cryptography called secure multi-party computation. What you're going to do is have the server and all of your clients collaborate with one another, and they're going to cooperatively simulate this trusted third party. And as long as enough of these participants are sufficiently honest, and we can put exact meaning to what I mean by enough and sufficient, you can prove that the privacy properties are the same as in the trusted third party situation. So this version, especially in the situation where you're doing the cross-device federated learning, this is, in some sense, it's the most challenging, but it's also the most flexible. It's the easiest to deploy. You don't need any special hardware. And so this is where I'm going to dive in now for this tutorial. So in particular for federated learning, we have this aggregation operation. And so secure multi-party computation for aggregation goes under the heading of secure aggregation. And this is a problem that's been studied for a while, but particularly for federated learning, what we really need are solutions that are both communication efficient for vectors and tensors, as well as robust to clients going offline. So these are mobile devices in the cross-device setting, and they will disappear at all points in time. Very reliably, they will disappear while you're trying to work with them. So you really need these robust, efficient protocols. So I'm going to walk you through one version of a robust, efficient protocol for secure aggregation. It starts by considering your set of devices. Here we have Alice, Bob, and Carol. And what we're going to do is have each pair of devices cooperate to sample a random vector, actually a pair of random vectors that add up to 0. Okay, so what we want is Alice and Carol to end up with each of them with a vector, and one of them is going to have the positive version of that vector, one the negative version of that vector. So when they add together, they sum to 0. We're going to have each pair of devices do this. And so you can think about these vectors as kind of antiparticles. If you ever add them together, they're going to cancel out. Each pair of devices does this. And then when the devices go to submit their values to the server, they will take their parameter vector or their model update vector and add their mask, all of their half of these masks to it. Okay, so the random vectors that were generated were the same size as the model updates. And now if you look at the contribution from, say, Alice, her contribution is completely obscured in the cryptographic sense by these random masks that she's added. However, once the server adds all of these values together, there is the inputs are completely masked. The random masks completely cancel out, and the value that comes out the other side is exactly the aggregate that the server was trying to learn. So this all works great. However, there are still a couple challenges. The first challenge is that these random vectors are large. How do the users efficiently agree on them? Remember that these are the size of the model parameters. The second question is, what happens if somebody drops out? So if Bob happens to not submit his value before finishing the protocol, the masks that Bob was supposed to contribute to cancel out some of the masks in Alice's and Carol's contributions, they never get added into the sum. So the final sum that the server produces still has these random masks in them, and that's not good. So what can we do to solve these problems? So to solve the first problem, we're going to start with digging into a little bit of how the masks the pairwise masks are generated. It starts by having each of the clients choose a random scalar secret, represented by these letters A, B, and C here. And what we can do is a protocol called Diffie-Hellman key agreement. We take the secret and we run a procedure on it that lets it be revealed publicly. So you can think about this as taking a publicly known value G and raising it to the power of the secret. And this, you can show that this is cryptographically hard to recover the secret if you only know, say, G to the A. Each of the client devices can send this to the server because they're public, and the server can distribute them out to all of the other devices. So now Alice knows the public versions of Bob and Carol's secret, as well as her own private secret. Meanwhile, the server is going to retain a copy of all of the public information. Now Alice can take, say, the public version of Carol's secret, that's G to the C, and combine it with her own secret by further raising it to her secret's power. So she can compute G to the B to the A, which is G to the B times A, and she can compute the same thing with respect to Carol's secret. Now, Bob and Carol are both doing the same thing, and you can see, because of the commutativity of exponentiation, that Alice and Bob end up with a shared secret here, that is G to the A times B. So now each pair of users has a shared scalar secret. So these secrets are scalars, but they can be used as the seeds to pseudo-random number generators in order to expand the secret to the size of the model parameters. And then we just need to have each user have each pair of users agree that one of them will take the positive version and one of them will take the negative version. And at that point, we have all of the vectors distributed, even though we only had to pass a small handful of scalars around the system. Okay, so this, we have efficiency via the use of the pseudo-random number generator. There's very few secrets in this system, just these A, B, and C. So that's going to make our recovery problem easier in a moment. And yes, we had to pass everything via the server, but actually, given the way that mobile phones communicate anyhow, it's almost impossible to avoid that in the first place. So how can we do the recovery? This rests on a piece of cryptography called threshold secret sharing. And the idea in K out of N threshold secret sharing is that you're going to take some secret and break it into N pieces called shares, and do it in such a way that if you have fewer than K of the shares, you can learn absolutely nothing about what the secret is. But as soon as you are able to assemble at least K shares, you can recover the secret perfectly. And so as an example of how that might be possible, you can imagine a secret, say S, and you can imagine saying, I'm going to randomly sample a number of lines that all intersect at a point whose X coordinate is the secret that I'm trying to protect. Okay, so you can see that here, the secret S along the X-axis and all the lines intersecting there. Now, any party who has just one of these lines, the lines represent the shares, knows absolutely nothing about where that intersection point is. But as soon as the party gathers at least two lines, it can find the intersection point and learn exactly what the secret is. This is a simplified version, but you can extend this to any number or to any K and N. Okay, so how do we use this? Users are going to take their secret value, their secret scalars, and create enough shares of those secrets, one for each user in the system. Then they're going to pass those secrets out early in the protocol. So now every user in the system has a share of each secret. Later on, when Bob drops out, the server can come back to the remaining users and say, hey, could you please give me shares of Bob's secret? And the remaining users share those pieces of Bob's secret. The server can reconstruct Bob's secret value B and use it to essentially simulate what Bob should have done, assuming that Bob had a zero valued input. So this lets the server generate the masks that would have been produced by Bob, cancel them out in the sum, and get a result, adding only Alice and Carol's value together. So this is great. As long as there are enough honest users in the system, and as long as you set the threshold high enough, you can prove that the dishonest users, even if they collaborate with one another, won't be able to reconstruct any of the secrets. However, there is still a problem. What if Bob actually didn't completely disappear, but just was submitting his value late? In this case, the server has learned the masks that were supposed to be protecting Bob's secret, and now can strip those protections off if it wanted to and learn Bob's secret. And we'd like to prevent that from happening. So what we're going to do is go back to this point where all of the users are generating masks and ask each of them to generate one additional mask. This is a personal mask that is not in a pairwise relationship with anybody else. When the users are generating shares of their secrets, they're also going to generate shares of the seed for the random number generator that produced their personal masks as well. So now there's two kinds of secret shares in the system. And the users are going to pass out shares of each kind of secret to all the other users. So now each user has a share of each of the two kinds of secrets for each user in the system. Later on, when the users have all made their contributions and after Bob has dropped out, the server needs to be able to strip off the private masks, the personal masks for Alice and Carol, as well as the pairwise masks for Bob. So the server asks for shares of Alice and Carol's personal mask secret, as well as shares for Bob's pairwise mask secret. Having gathered these shares, the server is able to reconstruct the personal masks for Alice and Carol, as well as the pairwise mask for Bob, and strip off all of these contributions, leaving exactly the value that it's interested in. However, when Bob's contribution arrives late, the server has only reconstructed the secret that led to Bob's pairwise masks, not his personal mask. And so that personal mask is permanent from this point on. As honest users in this system will only give out shares of one or the other secret, never shares of both secrets with respect to the same user. And so because the server is able to reconstruct Bob's pairwise mask, it'll never be able to reconstruct Bob's personal mask. In the end, we end up with a protocol that's secure against a third of the clients being malicious and cooperating with an adversary that fully observes everything that happens on the server. It's robust up to a third of the users dropping out during the execution of this protocol at any point during the protocol. It's communication efficient. So for 1 million model parameters, 16 bits per parameter, 1,000 users, you're expecting to transmit about 75% more bits than you would if you just ran this in the clear. And it's a cryptographic protocol that is computationally efficient over up to about 1,000 clients, and it runs over 4 rounds of communication. Now, the reason I say over only up to about 1,000 clients is because some of the computational steps in this protocol scale with the number of masks and the number of secrets shares being exchanged in this system. And as I described it earlier, every client is sharing secrets with every other client in the system. So if you take these circles to be clients and the edges to be the places where secrets and masks are being used, you can see that the amount of work here basically grows with n squared. So that was the state of the art in 2017. In 2020, we published an extension to this work that showed that you can actually run exactly the same protocol on a much sparser graph and get almost the same security guarantees. So in this situation, we're going to take a graph that has n clients, and each client has exactly k neighbors. We'll assume that the clients are randomly assigned to positions in this graph, and we're going to take the number of neighbors to grow with the log of the number of clients. And you can show that in this arrangement, you can prove that the security guarantees that I talked about earlier continue to hold with extremely high probability, with cryptographically high probability. It's essentially just as likely that you're going to randomly guess one of the crypto keys in the protocol as it is that the other security guarantees won't hold on this, this much sparser graph. So what that means is now if you start looking at things like the computational cost at the server, rather than having the computational cost grow with n squared times the length of the vector, where n here is the number of users, it grows with n log squared n. That is a much more efficient growth. Similarly, at the client, the computation factor goes down quite a bit as well. And the communication factors likewise go down somewhat because each of these parties is distributing secrets to fewer other parties. In the end, we end up with a protocol where if you wanted to say aggregate over 1 billion clients, in the complete graph version, you'd have to run over 1 million, essentially run the protocol 1 million times, each over about 1,000 clients. But with this extension, you could run over a single cohort of 1 billion clients and have it cost less than doing those million cohorts in the previous version. Okay, so that is dense secure aggregation. However, there's actually some really interesting places in federated learning where sparsity comes up. So for example, consider that you're trying to train an embedding-based model, say a natural language model that has one embedding for every word in your vocabulary, or an object recognition model that has one embedding for every object that you want to recognize. Or say that you're trying to work with some form of compound model that has multiple copies of the same model, say a pluralistic model, or a model that has one copy of the submodel for every genre or cluster or location or company that you're trying to train over. Or say that you're doing federated analytics and each device is only going to be contributing values to a small handful of the bins in a histogram. In all of these situations, what you really want to be doing is some form of sparse federated learning that has sparse aggregations in it. So really what we'd like to do is take this picture that we had earlier of federated learning and ask, well, if the client device only has information that's relevant to a portion of the model, is it possible that that device could get access to just that portion of the model that it has information for? And so download only that portion, train only on that portion, and then contribute an update that's kind of scaled to the size of the portion that it was going to update. And really, in a lot of cases, the portion of the model that the client wants to update is also private. The portion of the model may be dependent on the client's data. So really what we'd like is private versions of each of these operations. Let's start with private sliced model download. So there's a branch of secure multi-party computation called private information retrieval that actually lets us do that. I'm going to give you a brief walkthrough of how this might be possible. So imagine that on your server, you've assembled a vector of model slices where each slice of the model is thought, you can think of it as one element of this vector. And then your client device creates a one-hot vector where there's a 1 in the location corresponding to the model slice that it's interested in. Now, if it was safe to transmit this vector in the clear, you could just have the client device upload this vector. The server could take an inner product with that vector, and the result would be the model slice that the client device is interested in. However, if we want to protect the privacy of this model slice, what you can do is have the client encrypt this vector using a homomorphic encryption system. So a homomorphic encryption system lets you do certain kinds of arithmetic operations while keeping the data that you're working on encrypted. So here the client is going to encrypt the query vector, upload it to the server. The server then can compute this inner product without being able to decrypt the query vector at all. And it produces an encrypted version of the model slice that the client device is interested in. The server can then send this encrypted version back to the client, and the client has the key to decrypt it. The server learns absolutely nothing about which slice the client device is interested in, but the client still gets exactly the slice of the model that it needed in order to compute the sparse model update. Let's turn now to private sparse aggregation. So this is a challenging problem. I'm only going to show you one flavor of it, but for different patterns of sparsity, you're probably going to want different solutions. Here, I'm going to show you a version that lets us build a shuffler on top of the dense secure aggregation protocol that I described earlier. And the basic idea is, imagine forming a dense vector where each element of this vector is going to be the size of whatever messages you want to be shuffling. So we'll have each device choose a random slot in this vector and form a model update that writes zeros to all the other slots, but the message to the slot that they're interested in. You can then run the dense secure aggregation protocol on top of this and get a vector that has a handful of zeros, but also a handful of messages in it. And this works as long as every device happens to randomly choose a different slot. However, because of things like the birthday paradox, it actually turns out to be quite likely that at least some of the devices are going to end up choosing the same slot as other devices. And so in these situations, that conflict means that neither of those messages, the blue and green message in this slide, would be recoverable. Is there a way to do better? The answer is yes. We can use a data structure called an invertible Bloom lookup table. And the basic idea here is we're still going to use a big vector, but now the slots are going to be the size of a pseudonym plus the random message. So what we're going to do is have the clients choose a pseudonym, which is just a random number. And the client is going to take their pseudonym and apply k-hash functions to that pseudonym in order to select k different slots in this random vector. And then into each of those slots, the client device is going to write the combination, the concatenation of their pseudonym and their message. So just as before, there's going to be some conflicts. In fact, there might be slightly more conflicts because you're now writing more elements into this vector. However, there are going to be some slots where there is an unconflicted value. So what we can do is the server, for any unconflicted slot, the server is going to be able to recover the pseudonym message pair from those slots. And then because the server also knows the hash functions in this system are public, the server can figure out all of the slots where those pseudonyms would have had their messages written. And so it's able to subtract off the contributions from those slots. This leaves some slots that were previously conflicted are now deconflicted, and the server can now read out those messages. And you can just repeat this procedure until either all of the messages are extracted or no more progress is able to be made. So kind of the unexpected outcome here is that if you analyze how many slots you need in order to make this work, really a vector that's about 1.3 times the number of messages you're planning to send through this shuffler is sufficient. You really don't need that many extra slots in order to make this system work with extremely high probability of recovering all of the messages in the system. So this is one way to build a shuffler on top of a dense aggregation procedure. And you can think about shuffling as being very similar to sparse aggregation, sparse histogramming as well. If you imagine saying, OK, what I'm going to do is use the shuffler to sum up, say, the set of indices that need to be incremented. So if a client wants to contribute a 1 to a sparse histogram in a particular slot, it just sends the index of the slot that needs to be incremented through the shuffler. So there's really a duality between shuffling and sparse histogramming. With that, I'm going to turn the presentation over to Peter to talk about differentially private federated training.
Thanks, Kallista. Do we want to take questions, or should we dive into?
So there was just this one question, which might actually have been answered, but you might want to check it. So I'm going to read at least the second part of the question. So the question started by saying, how do you learn to calculate the masks among more than 2 parties at scale without a server? And I believe you have covered that aspect. But then the question continue and say that there is a DPSI protocol for privacy preserving abuse detection using DH with short signature, but there are security bounds to the protocol approaches due to confirmation attack possible on the blindness list of contacts. Could I possibly attack this scheme with such type of attack over masks?
I'm not familiar with the particular attack that's being referred to here. My first guess would be no, but I'd want to read in detail about that particular attack to make sure that I understand the details of it. In the system that I described, the masks should be essentially random vectors. You do need to be careful that you don't draw too much randomness from any given seed, but you can quantify how much randomness is safe to draw from a cryptographically secure pseudorandom number generator. And the Diffie-Hellman assumptions, I believe, are proven secure in our CCS paper, but I would want to make sure I really understand this particular attack before making a strong statement.
Fantastic. Thank you.
All right, I think we can continue to the third part. So we saw secure aggregation, and secure aggregation is great because it hides the individual updates that from the server. So the server would not be able to inspect the individual updates, but the server would still be able to learn the aggregate, which in some cases, as we know, could still leak possibly sensitive information about participants. Those models tend to sometimes overlearn or memorize unique training examples. And this is where we can use differential privacy in order to prevent the model from memorizing. So I'm assuming a lot of you are familiar with differential privacy. I'll try to go quickly over the definition of differential privacy. So at a high level, differential privacy is just the statistical science of trying to learn as much as possible about a group while learning as little as possible about any individual in it. And so this is how we think of differential privacy. Assume you have a data set D of users. Let's say I'm one of the users in this data set. So there's training examples in this data set for me or from me. And let's say the query that we're applying on this data set is we're trying to train a machine learning model, a neural network. Now, assume you take me out of this data set. So you obtain data set D prime, and you still apply the exact same query. You want to train the exact same model. But now on the data set, the exact same one D except for me. So no Peter data in this D prime data set. Now, if the new model computed on data set D prime differs from the model that's computed on D, an adversary who somehow colludes with everybody except for me can look at M of D prime and figure out that I participated in the training of M D prime. In fact, it could be even worse because the adversary can learn my data or something or some feature about my data, which is problematic. So that's why in differential privacy, we want to try to give protection against such a strong adversary that has a lot of compute power and collusion power. And the one first thing that we notice here is that if we want to provide protections against such a strong adversary, we would want the training process to be randomized so that there's no one exact answer under the data set D prime, one exact deterministic answer, and likewise one exact deterministic answer under data set D prime. Because if that's the case, then it will always be that M of D and M of D prime are going to be different. So we will never be able to protect against such a strong adversary. So that's why now we think about M of D and M of D prime as essentially randomized models. So they are described by a distribution in a high dimensional space. And what differential privacy says is that the distribution of M of D and M of D prime, they have to be close to each other. Because the closer these two distributions are, the harder it is for an adversary to distinguish whether the model came from data set D or D prime. And that's the holy grail of differential privacy. And so the way this distance is measured is shown on the bottom of this slide. It's not very important for this talk, but it's a way of measuring distance between distributions, and it's captured by two quantities, epsilon and delta. Typically, we want delta to be cryptographically small, something like 1 divided by the number of training examples in the data set. And we want epsilon to be roughly in the single-digit regime. There's a lot of debate about how to choose epsilon. This talk is not going to attempt to even settle that debate about how to choose epsilon. Now, I want to try to distinguish between two flavors of differential privacy. The first one is called record-level differential privacy. This is kind of the more common notion of differential privacy. Here, the difference between dataset D and D prime is only in a single record. So what you do is you just change one row in the dataset when you go from D to D prime or the other way around. And in federated learning, typically we use the other notion, which is user-level differential privacy. And under user-level differential privacy, instead of just changing one record when we go from D to D prime, we change all the records that belong to a particular user. So you can see that now the notion of privacy or the unit of privacy is the user rather than the record. We're not trying to protect from an adversary that's trying to figure out whether or not a particular record was used, but rather we're trying to protect from a stronger adversary that's trying to discover whether or not a user participated or some feature about the user's data. And that's why this is commonly harder to achieve in practice. But this is we feel the right metric for federated learning systems. All right, so with those definitions, let's try to see how differential privacy is used in machine learning. And this is, again, hopefully something you've seen in the course of this workshop. So this is how we do iterative training with differential privacy. This first step is we sample a bunch of users. And I want to stress uniformity at random for this part of the talk, and we'll try to relax that later. And so we will sample uniformity at random a bunch of users, and then we will compute the model updates on those users. The next step is to clip those updates. So those updates are vectors, and then we clip their L2 norm to a pre-specified quantity, let's say S in this case. After we do this clipping, we average those clipped updates from the client, and then we add Gaussian noise. So notice the two fundamental differences here. First, the clipping, and second, the addition of noise, which in this case is Gaussian noise. And so after that, we take the noisy averaged clip gradients, and we use that to update the model. And we can repeat this many times as we need in order for, say, the loss to converge. Now, even though this looks very easy, it's actually a little complex in practice, and a lot of things can go wrong because we need to make sure we're adding the right noise, we're doing the right clipping, and we're actually budgeting privacy. We know how to calculate, how epsilon and delta, how they grow with the number of rounds that we perform on this data set. And so this is a complex science of applying differentially private mechanisms and accounting for privacy. And at Google, we have open source TensorFlow Privacy, which we invite people to use and contribute to. You can find the white paper on arXiv associated with TensorFlow Privacy. But what I want to say is whether you use TensorFlow Privacy or any other package, because there are other packages that are quite good out there, just make sure you use a vetted and audited implementation of differentially private mechanisms, because a lot of things can go wrong in practice. All right, so what I've described was kind of at a high level for, in general, training models with DP is not necessarily just applicable to FL. So now let's see how we can put it into the federated learning picture. So this is, Brendan showed the slide early on in this tutorial. This is kind of the federated learning system with the server and the devices, so on and so forth. So how do we modify this to make the training kind of differentially private? So this is how easy it is. So what we're doing here is after we compute the update on the client, notice that we're doing the clipping. So this is the L2 projection, or to clip the model update so that it has a norm S. So we do that clipping on device, and then notice how we now still aggregate those clipped updates, and the server now adds the Gaussian noise upon aggregating those clipped updates. And obviously, you can repeat this process many times. So if you do this, you get a differentially private version of federated learning. And the same concept also applies to federated analytics as well. So this is how you would do it in practice. And I wanted to show you just like one example of what you may get as a result. So this is differential privacy for language models that are trained in a federated fashion. We're training an LSTM-based predictive language model. The model has about 1.35 million parameters, and we're training it on the Reddit posts dataset. It's keyed by authors, so we can actually do the federated training in rounds. And what I would like to stress here is that, obviously, the obvious thing from this slide is that if we add a lot of noise and say we clip very harshly, we're not going to get good performance. You can see those curves that are not achieving a great accuracy, like the top one accuracy. But notice that if we do things cleverly, and if we have enough users in the system, and this is important because we're going to use something called amplification via sampling, and this is something that Audrey talked about in yesterday's tutorial in this workshop. So if we have enough users in the system, we can achieve very good accuracy. As you see those top figures, the blue one especially, compared to the baseline, with very strong privacy guarantees. So notice that we're getting a single digit epsilon, which I said is quite good. We're getting something close to 1 or even 4, and very, very small delta if we have a large number of users. So this is an interesting concept in federated learning, which says that if you have enough users and if you have enough computational resources to run those rounds and to also aggregate over large batches, because that's an important quantity that we also need here, then you can get performance that is comparable with the baseline of no differential privacy. Now, this is great, But this assumes that the server is adding the noise on behalf of the users to ensure that the whole training process is differentially private. And in some cases, maybe we want to relax that assumption and to somehow not necessarily have to rely on the server kind of adding the noise on behalf of clients. So one way of actually avoiding this is to use local differential privacy. And this is something that Brendan touched on very briefly in the first part of this talk. So here what we do is we clip the updates and we add the noise on the client. And we add the quantity of noise that is needed to achieve the epsilon that we target. And this is great from a privacy perspective because now everything is done on the device. But it turns out there's a long line of research. It turns out that if you're trying to train these high-dimensional models with local differential privacy, you're not going to get good accuracy. It's very hard to get good accuracy, even if you have a large set of users for these high-dimensional statistics and learning tasks with local differential privacy. So it's quite challenging. So the question that we kind of want to think about is, we know that under central DP, we just saw that it's easier to get high utility with good privacy guarantees. There's still a lot of open challenges and questions, and I'll touch a little on them, but we know that it's easier to get good utility compared to local DP, which it requires, the nice thing about it is that it requires weaker trust assumptions. And so one question that is very interesting in this space is how do we try to combine the best of those two worlds? And one answer is to try to use distributed differential privacy. And to go back to a slide that Kallista showed, we have this, kind of three different approaches to distribute trust for private aggregation. And the one that Kallista expanded on is the use of cryptography and secure multi-party computation via secure aggregation. That's the one that I'm going to try to expand on in this talk, but the other fronts are also equally applicable for doing distributed differential privacy. So in this vision, in this kind of approach, what we would do is we would still clip and add the noise locally, so very similar to how we do local differential privacy, but we wouldn't add noise to satisfy any necessarily meaningful local DP guarantee. So the privacy that you're getting from a local sense may be weak, but once you've aggregated those clipped and noisy updates via secure aggregation, which Kallista described, what the server ends up seeing at the output of this secure aggregation protocol is the update, the aggregate, plus enough noise to satisfy strong central differential privacy guarantees. And so this is kind of cool because now you don't have to necessarily rely on the server adding noise always on behalf of the users. So let me show you one way of doing this. But first, there are challenges in doing that. And the challenges are that when we talk about distributed differential privacy, we want to make sure that we incorporate the fact that secure aggregation protocols, because they are cryptographic in nature, they operate on finite groups or finite fields. So they use finite precision, and we don't have arbitrary kind of precision to represent noise distributions. For instance, things like the continuous Gaussian cannot be just used out of the box. One has to be very careful. And we know that they use modulo arithmetic. So all these summations are done modulo the size of the group. And so that's important to take into account. And one could think of potentially just using things like discrete Gaussian, and this is something I'll expand on in a bit, but one has to be very careful because sums of discrete Gaussians is not a discrete Gaussian. So this is quite surprising. You're probably used to seeing that sums of continuous Gaussian is a continuous Gaussian. That's true. But sums of discrete Gaussian is not a discrete Gaussian. So it requires a very particular analysis of its privacy guarantees. And one could, for instance, use distributions that have finite supports. We've seen people propose things like binomial distributions, sums of binomials as a binomial, so you can analyze its sum and try to figure out its privacy guarantees. That's okay, but there are two problems with that. Finite support distributions lead to catastrophic privacy failures. You can try to control that, put it into the delta. That's good, but in some cases you may want stronger privacy guarantees, and because these finite distributions have these catastrophic failures, they don't satisfy things like ready differential privacy or concentrated differential privacy, which allow us to do very tight privacy accounting. So these are the challenges that we face, and I'll propose solutions in the next few slides. This is going to be a paper that's going to appear later this week on arXiv. It's called the Distributed Discrete Gaussian Mechanism for Federated Learning with Secure Aggregation. And let me show you the idea at a very high level. So the idea is, as we saw before, we're going to start by taking the model update, which is XI. This is a processing that's done on the client. And we're going to do the clipping. So we're going to clip the norm to S exactly as we saw before. But after clipping, we will discretize the model update, meaning that we will go from real quantities to integers. So we will do a mapping from the reals to the integers, and I'll talk about it a little in a bit. And when we are in the integer space, after we discretize the data, we add the discrete Gaussian noise. And finally, because we said that secure aggregation operates over a finite group, we do modular clipping. So we have to take the set of integers and somehow fold it into a finite set of integers. So modular clipping is going to be really important because we're going to have to use secure aggregation here. And so just to expand a little more on the discretization that we're going to apply, we have to be very careful, it turns out, because if you don't discretize the data properly, you suffer from inflating the L2 norm of the update, of the model update. And if that happens, you're going to have to pay a harsh penalty in differential privacy, because differential privacy, the amount of noise that you have to add is proportional to the L2 sensitivity of these vectors that you're trying to aggregate. So you want to make sure that how you discretize the data preserves that L2 norm as much as possible. So it turns out in order to preserve the L2 norm, what you have to do is you have to scale the data appropriately, and you have to do some random rotation to kind of flatten and spread the energy of the vector across all the coordinates. And then you can do something like randomized quantization to map to integers. And again, the details, you can read a lot about this. The details are in the paper. And once the server sees the aggregated noisy integers modulo the size of the group we're operating on, thanks to secure aggregation. This is shown in this box on this slide. It does a post-processing, and this post-processing is simply just to undo the discretization. So we're moving back from integers to reals. And you can see that what we're doing is just basically the inverse chain, which is dequantization, and then inverse rotation and inverse scaling that we did. Now, I want to show you some performance here. Again, one has to be careful because sums of discrete Gaussian is not a discrete Gaussian. So the privacy analysis, combining it with the modular clipping operation, has to be done carefully. And I invite you to see it in our paper that's going to appear on arXiv later this week. But if you do everything right and you put it together nicely, you'll get the following performance. This is the federated EMNIST dataset. It's a dataset. It's very. You may be very familiar with the MNIST dataset. This one is bigger because it not only has digits in it, it has digits and letters. So it has 62 classes. So it's kind of a slightly harder task. It has at least more classes in it. And the data set is grouped by the author writers, the writers of those digits and letters. And it has a total of about, actually exactly 3,400 clients. And in this training, we used 100 clients per round, and we're sampling uniformly at random in this experiment. We're training a model of size 1 million parameters. And as you can see on the plot, we're targeting a user level epsilon of 10. Again, this is different from the record level epsilon. And you can see that essentially with just 14 bits, so this is the size of the group that secure aggregation has to operate over, we can get an accuracy that matches exactly the centralized continuous Gaussian. So we can relax those trust assumptions drastically. We can get this distributed DP guarantee without suffering the accuracy. In fact, you can do this on an even more challenging task. This is the Stack Overflow data set for tag prediction. Now you have a lot more clients, and we're using 60 clients per round. The model is much bigger. It's 5 million parameters. And you can see again that with about 14 or even 16 bits, you can get essentially the same performance, or very close performance to the centralized continuous Gaussian, while using this distributed discrete Gaussian mechanism. And we're doing it here for epsilons 2.5 and 5. Those are user level DP epsilons. All right, so you can see more in the paper. In this final bit, I want to talk a little bit about how do we obtain precise DP guarantees for real-world production systems of cross-device FL. And remember I said when we train with differential privacy, we have to sample clients uniformly at random from the dataset. That was actually step one. And that's important for us to be able to use amplification via sampling guarantees, which are important in DP-SGD to get those good accuracy privacy trade-offs. But this presents a challenge for federated learning systems, actual deployments. This is because we don't even know the database a priori. It's not fixed. There's no known population size or fixed. Even those clients, they're not always available in all rounds. So we cannot just sample from them uniformly at random. It's very challenging to attempt to even sample from devices that are not available or devices that you are not aware that they might be available in the future. And even more importantly, even devices that you sampled can drop out in the middle of the execution of the protocol. So they can just disappear and go offline. So for privacy purposes, we want to model the environment as the choices of nature. So we want to try to assume that the nature can do all these malicious things, and we would love to be able to be robust to the nature's choices. So we want to get good privacy and utility guarantees regardless of what the nature chooses. And we want to be able to have algorithms that are self-accounting in the sense that we can calculate precise and tight bounds on the epsilon and delta that we get, regardless of what nature chooses. And we want the participation of devices to be mostly localized in the sense that we don't want the server to engage in very complex orchestration schemes to share randomness and to select the best solution would be one where the device itself could decide based on local information when to participate and if to participate. And obviously the last thing is we want to achieve those good privacy utility trade-offs that we see under DP-SGD, which is how we train in centralized fashions. So this is kind of the space of algorithms that we think is going to be really important in practice to go about this problem. So what we want is an iterative protocol. That's why we have protocol steps, T1, 2, so on and so forth. And in each step, nature, and this could be a malicious choice, chooses the set of available clients. So that's why C available here is a subset, could be a strict subset of the entire population that's out there. And the entire population is not necessarily known to the server. Now, out of those available clients that are online and they are eligible to participate, what should happen is that they should run a local routine. This is called should check-in on whatever randomness is available to them, and they should decide whether or not they want to check into the server. So this routine is going to give us the checked-in set, which is a subset of all the available devices. And those are the devices that check into the server that say, hey, I'm available, I can participate. And then on the server, from the set of checked-in devices, the server would select a subset of them. It could do something like random or deterministic, but that's the routine called select from, and that is run on the server. And now that we've selected those clients that we want to engage in the training round, out of those selected clients, only a subset is going to really, at the end of the day, report its updates because some may drop out, may go offline for all kinds of reasons. So you get a reported set. Those are the clients that finish the computation and do any operations needed and report back to the server. So then what the server ends up seeing essentially is the local update that was done on the reported set of clients in aggregate, because say we're using secure aggregation and something like distributed differential privacy. And what we would like is that this trace of XTs, the aggregate, we would want to be able to release that trace fully, and we want that to have precise epsilon delta differential privacy guarantee. So the server could update the model based on that trace of XTs iteratively. And at each step, we output theta t, or theta t plus 1, and we can quantify precisely what the privacy budget is so far. Now, in a recent work that appeared in NeurIPS 2020, we presented a new paradigm of amplification. It's called amplification via random check-ins. And I invite you to check the paper, but the main idea here is that the users, the available users, can decide when to participate. They can randomize across the training grounds, so they can choose essentially when they might want to participate and whether or not they want to participate. So they can subsample whether or not they want to participate and when they might want to participate. And we proved that this way of randomizing, which we call it random check-ins, gives you amplification guarantees that are on par with amplification via sampling or amplification via shuffling, which are necessary to train high-quality models. So you can learn more if you check that paper. All right, so this concludes the privacy part. In the interest of time, I will cover in 2 minutes some of the other interesting topics. This tutorial focused largely on privacy, but there are other very interesting questions. For instance, one of them is how do we improve the efficiency and effectiveness of federated learning? There are many interesting questions, things like how do we personalize the models on device to give better performance for each individual? How do we reduce wall clock training time through compression schemes? How do we make sure that we debug faults and mistakes, detect them? This is a challenging one because the server is not allowed to inspect the data, doesn't know exactly what's going on where, so we need solutions for those, so on and so forth. Training unsupervised reinforcement learning, all kinds of models on all kinds of data sets. What do we do if we only have a little labels, no labels, so on and so forth? So these are all interesting questions that are open and that are interesting to study. Another set of questions that we think are very interesting is basically how do we ensure fairness and how do we address the sources of bias? For instance, on device, there may be a lot of biases in the training data. For instance, the amount of training example, the training distribution, shifts, and all these things, so on and so forth. Clients may not be always available. And for instance, depending on who's online when, we may get to see different distributions, and that can cause sampling bias in the training process. So there are a lot of very interesting questions on the fairness and bias fronts that we also invite researchers to look at and try to address. And the third and last area that we think is really interesting is to try to have protocols that are robust to attacks and failures. So many things can go wrong. There could be bugs in the pre-processing pipelines, and those could lead to major failures. The model suddenly could have a loss that shoots up, or training can abort or fail, and we want to be able to be robust to such failures. Or even, some maliciousness can be injected into the system. Some devices may be compromised by a malicious agent, and they could be running a different protocol or injecting poisoned data. And so we would love to have a class of algorithms that are robust to these attacks and failures in practice. So there's a lot more that you can read. I invite you to check our paper, Advances in Open Problems in Federated Learning. There is now a new version of it that also includes new topics like system-level challenges and open questions. With that, I'll stop here, and thank you all for attending the tutorial. I'd be happy to take questions.
Well, thank you, Peter. I think that was an outstanding tutorial with a lot of interesting open issues that would provide research topic for many of us. So it's extremely interesting. And I think you did an incredible job in framing them. We have some time, about 3 minutes, for additional questions. I know some questions have already been answered in the chat, but are there any other questions?
Hi, thank you very much for the great talk. I just had a question from Peter. I didn't get exactly the motivation for discretizing the noise. So is it because if we, after adding continuous noise, if we do discretization before aggregation, we violate privacy assumption or something, or?
That's a very good question. So if you add continuous noise, say continuous Gaussian noise, and then you discretize, if the discretization is extremely fine, meaning that you have a very large number of bits, say 32 plus bits, then things would still go through. In fact, we could show that the DP guarantees would still hold, but that only assumes that you have a very large number of bits. So your discretization is very, very fine. Now, what we're trying to do here is we're trying to also achieve communication efficiency, because we don't want to represent necessarily each element of that vector with such a large number of bits. We want to do something like 16 bits or 14 or 12 bits, as I showed in my results. In that situation, when you go down to like 16 bits or well below the 32 level bits, then you cannot show the DP guarantees anymore. This discretization after adding the noise, the continuous noise, is not going to give you the precise differential privacy bounds that you look for. So one has to be careful, and that's why we're taking this very different approach to distributed differential privacy.
Thank you.
So Peter, we have a number of questions that just popped up in the chat. If you want to answer them, I think that would be great.
Sounds good. Yeah, I can try to address them if we're running short on time.
So there are two different questions by two different people, and David also, thank you for the great lecture.
I can maybe jump in. There's a question about considerations for choosing a communication framework when building a real-time system. I don't know actually that there's too much to say about that, other than you obviously want as little latency and as much throughput as possible, particularly if you're doing model training. There's a certain number of iterative steps you're just going to have to do in order to train a high quality model. So for those applications, it's really important that you can close rounds as quickly as possible. Generally, we would want to use, say Wi-Fi networks and do as much as we can, things like compression on the wire, maybe aggressive model compression, in order to minimize the communication latencies. Maybe I can just take the next one as well briefly. Other than for deep learning models, can we train other ML models which aren't based on stochastic gradient descent? So decision trees, naive Bayes, and so on. I don't know that we have a complete answer to that question, but often the answer is yes, but it may take some more algorithmic work, some changes to existing algorithms. So, on the one extreme, a lot of simple kind of statistical models can actually be viewed as instances of federated analytics, where you can just kind of get the right counts of the marginals you need, and that gives you a sufficient statistic for the model you want. So certainly things where all you need to do is count, yes, we can definitely do counting as kind of a federated computation using the same kind of infrastructure we use for federated learning with gradient descent or or federated analytics. In other cases, you need to kind of maybe come up with slightly modified versions of the algorithms that separate out kind of more clearly what runs on the client and what runs on the server. So I'm not sure about any work on decision trees. I suggest I think that's probably possible. I mean, in fact, some of the work that Peter briefly mentioned on private heavy hitters is basically a federated algorithm for building a tree, where clients kind of in each round vote on which leaves of the tree to grow. It's not exactly a decision tree, but I expect an extension in that direction is possible. And certainly it's also possible to run algorithms like k-means clustering, for example, where the server broadcasts out the current cluster centers, and then clients kind of contribute updates to those cluster centers based on which current center they're closest to.
Maybe I jump in if there's another question for the moment. So, well, firstly, thanks for the amazing tutorial. I really enjoyed it. So maybe this is a question for all three of you, and so that this technology has taken over in many applications, but what do you think is the next challenge? Where do you think is this technology? Where do you think it will go? So there was very recently an article that was mentioning the possibility of this application to replace cookies, and I found it extremely interesting. So could you give us some insight of where do you see these deployments here to go in the future?
Yeah, I can try taking an answer to that. I think it's specifically in reference to that article. I think federated learning is a piece of a bigger story where we start to think about trying to do keep the data closer to where it's being generated and minimizing the number of times you need to pass it around, minimize the amount of data you're passing it around, minimizing the number of copies. And so federated learning is interesting on its own. I think it's also most interesting when you think about it in combination with where are the other places where data is moving that we might be able to get away without moving it. There will likely need to be other technologies built alongside of federated learning to support some of those use cases. And I think that's a really interesting future direction.
Thank you. And maybe I can ask another question, maybe a little more technical question to Peter. So you have this step for the discretization mechanism where essentially you rely on this discretization process. I wonder whether, is this discretization process unbiased?
Sorry, is this discretization process what?
Unbiased.
Oh, this the one that I presented is biased. So the one that I had in the algorithm, I didn't describe it in full details. There is a bias because we're doing conditional randomized rounding in it. But in our experiments, we actually noticed that that bias, first of all, it does not impact the accuracy of the model. So even though we introduce a little bit of bias, please keep in mind that when we do L2 norm clipping, so even if we forget about distributed differential privacy altogether, when we train with DP, we have to do this L2 norm clipping, and that introduces a little bit of bias, but that ends up not hurting the model accuracy in itself, if done properly. But it turns out that we can discretize in an unbiased fashion, and that would still work equally well. So we can, instead of doing the conditional randomized rounding step, which I did not describe in details, we can do just randomized rounding, and that works just as well.
Okay, thank you.
Thanks. That's a very good question.
And I guess maybe one thing that we could do if the audience has a further question, we can and they will appear here in the chat. If you're okay with that, so we can send you an email with those questions, and then you can take your time to answer to them as well.
Perfect. Yeah, thanks a lot. This was fun.
Yeah, thank you, Brandon. Thank you, Kallista, and thank you, Peter, for an amazing tutorial. We really appreciate you taking the time in your busy schedule to give us all these insights. So thank you very much. I